Good morning, all. I just shared presentation. Am I audible and is it visible?
Yes, sir, it is.
Okay. So let us continue. So I think the previous lecture we have discussed this part. So let us start from this queuing diagram. Okay. So operating system maintains different queues. For example, here you can see the ready queue is there. Let me use the annotation tool. So this one is the ready queue. Okay, all the processes, they are having all of the resources except only one, and that is the processor, CPU. Okay, so process is eligible for execution because it has acquired all of the required resources. So all such processes are stored in the ready queue. So that is the ready queue of your process. Now, once it is scheduled by scheduler, then it goes to the CPU here. Fine. So such state of process is running. Now in running state, if that process needs some sort of IO, if that process needs some sort of say waiting for some event to happen. Okay. Now let us first upon see for the IO request. So process from the CPU will go to the IO request, and depending upon what kind of device is there, whether it is input device or output device, then for that we have a device queue. So that is input output queue. Once that IO is finished, because it is actually happening simultaneously with your processor, and if that is finished, then process again goes back to the ready queue. Again scheduled moves to CPU, something like this. If we are making use of time shared system and whatever the time quantum assigned to my process is finished, now it is turn of another process. Now my running process has to be interrupted. Okay, and that interruption is here. Like for example, time slice is expired, so it is actually not waiting for anything else, but such a process is interrupted and it will go from running to ready via this path. Again, whenever turn of that process is coming, it will go to running state, that is the CPU. Next one is, like for example, this is one special case, fork a child. Anyways, we are going to see the forking part in depth, even with example in C language. So fork a child is like creating a child process. So if process executes fork system call, then such a process first upon child executes. Now both become ready here. Both. So this child process is also will be in the ready queue. Next, if you are waiting for some sort of interrupts, Then again, if that interrupt is occurred, especially we'll see those examples of inter-process synchronization where we need to synchronize execution of multiple processes. So one process is depending on other process. So those steps will be implemented through interrupts. So if process is waiting for such interrupt, let me give a very simple example. If there is a parent process and if it executes the fork system call, now what happens with fork is it creates a child process. Now some task is given to child process, and whenever parent is waiting for completion of child, actually parent is waiting for the interrupt, and that interrupt is like child terminated. Okay, so this is the representation of different uh, queues. Okay, so typically used for the process scheduling purpose. Let us move to the next. These are different types of schedulers. Now there is always confusion between the types of schedulers and scheduling algorithms. See, types of schedulers is different thing and scheduling algorithms are different. Okay. Algorithms are the process followed by the scheduler. The process followed by the scheduler. Whereas the short term, long term, even medium term schedulers are also there. So let us start with the types of schedulers. So at the beginning we have short term scheduler. Okay. Still students are joining. It is exactly same thing happening like classrooms. Okay. Actually that is creating some sort of disturbance. So let us start with short term scheduler. The short term scheduler is also called as the CPU scheduler. Now the important word here everywhere is, now what is this term exactly? Because we are saying short, then long, and later again we'll add one more thing, something called as a medium term. Okay. So short term scheduler is, as I mentioned, it is also called as a CPU scheduler. Okay. And this scheduler's main task is to select the process the CPU scheduler's task is to select the process. Typically, it is called as a selecting next process because already one process is there. Okay, so select the next process for the execution. Obviously, the thing is the CPU scheduler or short-term scheduler will select the process from ready queue only. Okay, the process is having all the resources. Scheduler will never select the process which is waiting for interrupt to happen, or which is waiting for some sort of input output. Okay, such processes are not selected. So short-term scheduler always select the process from the ready queue. Okay, and even though we are going to see all three types of schedulers, maybe in a few operating system this is the only type of scheduler available. So this is mandatory. So CPU scheduler is mandatory because that will select the process for the execution. Now I was talking about the term. What is this term? Remember, this term is nothing but the frequency. How frequently this scheduler is invoked. Okay, and the short-term scheduler is the most frequent scheduler activated by the operating system, and that time is usually in milliseconds. And because this time is in milliseconds, that means this is more frequent. The important part here is, suppose we are making use of this short-term scheduler, say after each and every 5 milliseconds. Example I am saying, after each and every 5 milliseconds. Okay, and scheduler itself requires say 8 milliseconds, then this definitely creates a problem, because actual task will be executed just for 5 milliseconds, and selection of next task needs 8 milliseconds. So actually we are wasting time in switching between the processes. That is the reason the implementation of short-term scheduler must be fast. It must be fast. Okay, so it should be quick, maybe in a fraction of millisecond also, right? So that is what the short-term scheduler. Two requirements. Why this short term? Because it is more frequent. The time is in milliseconds. Second requirement is it must be fast. Okay, and this is the scheduler which will select the next process, or rather I can say it selects the process and allocates the CPU for execution. So that is the short term scheduler. Next is long term. Now, as the name long, its frequency is not that much quick. Okay, so frequency is typically mentioned in terms of seconds, even minutes. Okay, so it is infrequent, and because this is not that much frequent, it can be slow. Anyways, if it is also fast, no issues. Definitely that increases the throughput of your system, operating system, right? So long-term scheduler, like short-term scheduler is also called as a CPU scheduler. Long-term scheduler is called as job scheduler, where it will select the processes that should be brought into the ready queue, right? The processes that should be brought into the ready queue. So that is the requirement. So because ready queue, how many processes are there in the ready queue? Okay, this is typically called as degree of multiprogramming. How number of processes executing concurrently, that is the degree of multiprogramming. And whenever you are bringing the process into the ready queue, that means you are increasing the degree of multiprogramming. Okay, so the objective of long-term scheduler is not to assign CPU to that process. Remember, we are just taking the next job into our system. We are taking just next job into our system. So that is what the long-term scheduler is. Okay? So the ultimate aim of long-term scheduler is to control the degree of multiprogramming, depending upon anyways how many resources your system have. Right. Now, before looking at the medium-term scheduler, we need discuss two things. One is the IO bound process and one is the CPU bound process. What does it mean? So IO bound process means it is a process which is actually spending more time in say input and output than the computation. Okay, say for example, read 10 numbers, do it summation and display the result. Now reading 10 numbers needs more time than actually doing the summation. And maybe then we are just displaying it. Maybe formatted displays there. We want to have some sort of tabular displays. So that process is actually spending more time doing the input and output than the computation. Whereas you can think something like you are supposed to check a huge number and whether that number is prime or not. Now depending upon the number, because for example, imagine something like you are supposed to display the uh, prime numbers between 10 lakh to 15 lakh, 10 lakh to 15 lakh, right? Now in this, actually we are not doing any input output. No input at all. Maybe we are hard coded 10 lakh and 20 lakh, or maybe we are taking the start number and end number. So that is just the input, two inputs, and then we just want to display. But again, display is very small part. In this case, we just want to display the number. But now deciding whether that number is prime or not, we need to divide that number by 2, then 3, then 4, 5, 6, 7, 8, 9, 10, up to maybe mathematically up to it is the square root of that number, right? Now this computation, now if you want to check this part, if you want to check this part, how much time is required actually for calculation, you do very simple C program in which you try to divide that number by say 2, then 3, then 4, 5, 6, up to square root of that number. And whenever this program is doing calculation, try to make use of system monitor and check the CPU utilization. You will get near to 100% utilization. That means CPU is actually doing computation. And such category of process is called as CPU bound process. Got the difference between both? IO bound, in which process is actually spending more time on doing input and output. Okay. Whereas CPU bound process, it spends more time doing computations. Very few. And that actually is called as a CPU burst, because this word is later required. CPU burst. I just highlighted this CPU bursts. Okay. Now, long-term scheduler, it'll try to strive for good mix of process. There must be IO processes also, IO bound processes also, and CPU bound processes also. Then and then only we'll get better throughput. So, for example, if there is a good mix of IO bound and CPU bound, if process is waiting for IO till that time, we'll go with another process. Okay, if only CP bound is there, then definitely we are spending or rather wasting more time in scheduler itself. Fine. So the short-term scheduler is the CPU scheduler. The word term, short term, long term, this is related to how frequently that scheduler is activated by operating system. Okay. So short-term scheduler, long-term scheduler. Any doubt on this slide? If you have any doubt, either unmute yourself or put it on chat. No, so fine. So let us continue. Let us move to the next slide. Now here we want to talk about the medium-term schedule. So the medium-term scheduler, it can be added. See why the word can be added, because as I already mentioned, even long-term scheduler is also not mandatory. Only mandatory thing is the short-term scheduler. Okay, but whenever you need to decrease the degree of multiprogramming, decrease I am saying. Now you may wonder here, why to decrease it? Why to decrease it? Reason, as I mentioned, suppose there are just CPU bound processes and everybody is having task that has to be completed by the CPU. In that case, what happens is actually we are wasting time of processor switching between one process to other process. So we should have a proper mix that has to be decided by long-term scheduler. Okay, but then uh, there is question. What is this? Sir, please explain CPU bursts. Okay, CPU burst is nothing but for that much amount. So, say for example, I have 10 different tasks. I mean processor. Processor have to do 10 different tasks. Okay, and then all 10 are contiguous. So this block is called as a burst. Whereas you can imagine something like I have two CPU instruction, then one IO, again two CPU instruction, then one IO, then two, three CPU, again one, two IO. Now it is a mix, right? This is not called as a burst. Burst is what? Contiguously, there is a task for that CPU where utilization of CPU is more. That is the CPU burst. Is it okay? Omkar Talekar. Yeah, yeah, okay, fine. So let us come back to the medium term scheduler. Here, whenever we want to decrease, now why to decrease? Because maybe throughput is reduced. Maybe we are just wasting our CPU cycles to switch between the processes. Okay, in that case, medium term scheduler will be added. The task done by medium term scheduler is very simple. That is called as a swapping. Okay, swapping is not just swapping out because two things are there: swap in and swap out. If you look in the diagram here, so I guess I already mentioned what is the swap area. That is again important thing. Swap area is what? It is like a virtual memory. It is part of hard disk, actually disk. Okay, that we want to utilize as a memory. Memory is primary memory, RAM. Okay, so for that, like for example, if you have installed the Linux operating system, we create a swap partition for that. Okay, so medium term scheduler, here have a look at here. This is the swap space. The process is in memory. Now process can be taken out from primary memory to the swap. This operation is called as a swap out, and whenever you want to again take that process back, then the operation is swap in. So process will be taken from the swap area into again the ready queue. Okay, even though it is not shown in this diagram, if process is waiting and if we need memory, from this also we can take process. This is a swap out and this is also swap in, and this is usually done whenever we are in shortage of memory. So for example, memory is full and another process want to enter the operating system. That will increase the degree of multiprogramming, but there is no space. And if there is a no space, we need to swap out few processes from main memory onto the swap. So that is also the swap out. So waiting, maybe waiting processes are also selected. Most of the time this is not selected because what will happen if one process is waiting for say some sort of interrupt to happen, and if that interrupt occurs, then there is a more task to the medium term scheduler to check the interrupt is for which process, and if that process is not there in the primary memory, then it has to be taken from the swap. So typically the important interrupts are there. Such processes waiting for those interrupts will not be swapped out. They will be in the, even though they are waiting, they will be in the main memory only. So medium term scheduler, sometimes if we want to decrease the degree of multiprogramming, then processes may be taken out from main memory to partially executed but swapped out processes. This is the swap space. Fine. Is it okay? So now I can say there are three types of schedulers. Now here let me use text tool. So from ready queue to CPU, this is the short-term scheduler. Short-term scheduler will work here, right? Which will pick up the process from the ready queue and it will be assigned to the CPU. Now the long-term scheduler will be here, which will take the process this long-term scheduler will take the processes into the system. Okay. So this decides the degree of multiprogramming. Ready queue. Okay. And now here, swap out and swap in. So this is the medium term scheduler. So let me put it here. Medium term scheduler will be here also and here also. Okay. So three types of schedulers. Any doubt in this? Any doubt in this? Sir, will you please repeat the medium term scheduler diagram in short? The same thing, the medium term working here, taking processes from swap into the ready queue and running processes will be taken out on the swap. This has to be done by the medium term. Why to do this? To decrease the degree of multiprogramming. Why to decrease the degree of multiprogramming? Maybe we are not getting proper throughput. If there is no proper mix of processes. Okay, so it is not mandatory scheduler. It can be added. So let us move to the next slide. I think this was because of network issue, Shubham Jain was disconnected from the meeting. He has requested to join. Please accept his request. I am not getting any request actually. Because if somebody is waiting in the lobby, it immediately shows me and that I am doing. Okay, so if any request appears here, fine. I'm actually accepting everybody. No problem. I think this was the question asked by somebody in previous lecture. How multitasking happens in mobile system? Even the question was, do we have the PCBs there, process control blocks? I think they asked about the Android. But now example mentioned here is iOS. Like earlier versions of iOS, they only allow one process to run. Others are simply suspended. So there is only one process running at a time. Okay. Now, the foreground process and background process, two things are mentioned now. Let me select highlighter and okay. Now what is the foreground process? Foreground process is a process with which user actually interacts. Okay. So for example, this ZX process I am using right now is a foreground, but other processes are also running in the background. So background processes, yes, they are also there in the memory. They are also running, but not on the display. So I'm not actually interacting with that. Okay. So foreground process and background process. Okay. Now these two types of processes now later supported by iOS operating system. Now similarly for Android, background process uses service to perform tasks. So they simply called it as a service. Even if you think of Linux operating system, they are called as a daemon processes. Daemon, DAEMON. Okay. So Android call them as the service processes. Services can keep running even if background process is suspended. That is what happens with Android. And because they are in background, they actually do not have any user interface. The same thing in case of iOS also. Okay. So multitasking here also possible. Context switch, I think we already discussed this part. When CPU switches from one process to another process, the system must save the state of the old process and load the state of another process to which you want to switch. Okay, and this process is called as context switching. I hope we already gone through it. The context switch, this one. CPU switch from process to process, where old processes state will be stored, new processes state will be loaded, and execution of this new process starts. So this is called as a context switching. Right. Okay. Now the context of a process is represented by process control block, and we already saw what are the contents of PCB. All the CPU registers are there, then your program counter is there. So lots of stuff is there. So context of process is, I think there is question on chat. Okay, same question. What is the context? Okay, so context of process is represented by process control block. Okay. Now we say, let me tell you what is the context. If I ask you what is program, if I ask the question, what is program? Now, as I already mentioned, if it is course of say C++ programming, then what is program is .cpp file is a program. Okay. So it is like with respect to computer programming course, program is the source code. Now with respect to operating system, exactly same thing I am saying. In the context of operating system, what is program? It is not source code file. It is executable file. Got it? So now how a specific process is like whenever we are saying the context of that specific process. So that will be represented by PCB, process control block. And the contents of PCB we already gone through. This is the PCB, okay, where we have the state, PID, the program counter, CPU registers, list of open files, different memory limits. And these memory limits are nothing but whatever the four segments of process we discuss. The text region, then we have data, then stack, then heap, all that. So that is what actually process is, and it is represented by its context. So PCB is used for that purpose. Now, whenever we are switching, like meaning of that is very simple. For a processor, when processor is doing some sort of say single instruction A plus plus, think of C program where we use the statement A plus plus, right? Now A plus plus for a processor it is fine. For a processor it is fine. It is doing some sort of calculation, no issue. But then the question is A plus plus belongs to which process? Let me give very simple, even simpler example on rather than this. Imagine something like multiple terminals you have open, okay, and now I press, or maybe say in the terminal different processes are running there. Now if I press Control C, if I press Control C, now Control C is the input which is used to terminate the process. Now which process is terminated? That is important. So very simple thing, which is the interactive and foreground process. Okay, the process which is interactive. Somebody is saying running. Running I cannot say is the correct answer. Yeah, Rajvardhan, running is not the correct answer. Let me tell you why. You imagine you have executed a program, and in your program you displayed something like enter a number, okay, and now your program is waiting for some sort of input there, right? Now because your program is waiting for input, it is definitely not running, it is going back in the waiting state. And now whenever that process is waiting for that input, if I press Control C, no, because that is a foreground process, the terminal is attached to that, even though it is not running, it will be terminated. Okay. So now whatever the key combination you are using there, that will be taken by the process related to the context. So whatever the processor is executing, actually processor is executing for a specific process, and that is called as context of that process. Okay. So technically whenever you are switching from one process to another process, some time is required for that, and that is the context time overhead. Okay, and if there is a context time overhead, during that time operating system don't do any useful work. So that is actually waste of time. The CPU is not busy in that case, actually executing some task. Okay, more complex operating system with PCB, they will definitely take the longer time for context switching. So this part is important. It is overhead, right? So context switch time is overhead. I just give an example for the CPU scheduler. I just mentioned the same thing there. If my time quantum is say 5 millisecond and context switching takes 8 millisecond, then actually we are wasting more time switching between one task to another task. and we may get lesser throughput than serial processing also. Fine. Okay. Now, this time of context switch definitely depends on the resources, hardware resources. Okay. And like for example, few hardware provide multiple sets of registers per CPU. For example, if we have multiple CPUs, nowadays we have something called as symmetric multiprocessing. Multiple processors are available in your personal computer also. And in that case, with each and every processor, if you have multiple sets of registers, then it is possible to load the multiple contexts at a time, which will definitely reduce the context switch overhead. Right? So this is related to context switch. Now we want to see the operations on processes. Operating system is supposed to provide some sort of mechanism to create the process, to terminate the process, and so on. Maybe something like inter-process communication is also required, inter-process synchronization is also required. So many operations are there. One process should be able to send some sort of signal to another process. One process may want to terminate another process. So maybe process will be terminated on its own. Maybe process is terminated by somebody else forcefully. And if that is supported, we again need to manage the permissions part. Okay. Now let us start with process creation. In booting process, I mentioned the very first process. I think the PID of that process is one, called as init process. I mentioned init, INIT. This process has ID 1, PID 1. Okay, so that is the grandparent process, parent of all the process. Okay, actually it forms some sort of tree. So hierarchy is there. I think I mentioned there is one command called as a PS tree. PS tree, that is process tree, which will display that tree. Somebody asked the question, command is not working. I think he's trying to run the command on Windows operating system. The command is provided in Linux and Unix. So on Linux, if you try the command PS3, you can get that the tree of processes. Here, the relationship between processes is important, and that relationship is denoted by two words. One is the parent and one is the child. So the only way in Linux to create the process is by duplicating itself. A process can duplicate itself, and duplication is in terms of all the sections of memory, like text region is there, data region is there, stack is there, and extra is there. Okay, so here important thing is fork is the system called used for that purpose. Okay, now I just give an example from Linux, but our course is the generic operating system concepts, right? So whenever you think of formation of tree of processes, then two types of processes, one is called as a parent process, one is called as a child process. So important thing here is except init, each and every process must have a parent process. And why I am saying except init, because that is a grandparent process, right? So whenever any process creates a new process, newly created process becomes the child process, and the process who creates that child becomes the parent process. Okay. So anyways, we'll see practical example for that. But as I mentioned, for process identifier, PID is required for each and every process. Like as I mentioned, for init process, PID is 1. This is just unsigned number. So whenever you create a process, definitely PID is required. Process identifier is required for that. So that is about PID. Now, while creating the new process, the resource sharing options are there. Parent and children, they share all the resources. Children share subset of parents resources, and parent and child do not share any resources. So there are three ways actually. There are three ways by which we can share the resources. Now, if I want to give example from say Linux operating system, then parent and child do not share any resource. I just mentioned the child processes duplicate copy of parent. Even though it is a duplicate copy, at the time of creation of child, whatever the state of parent is there, that will be copied as it is, including everything. Your context of process, whatever the open files are there, everything. But in all that stuff will be in separate memory space. Now, only problem is whenever you have some sort of pointers, it is you imagine something like call by value and call by reference. What happens with call by value is we are sharing the value, but that value will be actually copied in another memory location. Exactly same thing happens. But what happens if we share the pointers? The same memory location will be accessed by the both. That is the only difference in the sharing. Okay. So whatever the resources, as I mentioned, we can create the child process, duplicate copy of parent, yes, no doubt. But then what about the resources? Now three options. Option number one, both can share all the resources. Number two, they can share few resources from parent. Number three, no sharing at all. Okay. Similarly, execution options are there. Parent and children execute concurrently. Parent waits until children terminate. Now again, if I want to give example from the Linux operating system, then parent and children execute concurrently, no issues at all. And parent waits until children terminate, no, programmer has to take due care for this part. Okay. So what I'll do is let me share. Let me open first of all. Just will try to write a small code here. For which let me share my. Is it visible? Is it visible? I just shared. Yes, fine. So what I'll do is let me make use of stdio.h. Let me check for the manual page of fork. See, unistd.h is the header file required for that. So fork is used to create a new process. Okay. So let me have that unistd.h hash include unistd.h. Then let us write the main program, and in this main program there is one data type called as a PID underscore T. So that is a type. Let me use variable called as a PID, and PID is equal to fork. So here I want to create, and just to show something, let me use printf. So printf say hello, and after fork what I'll do is printf say bye. All right. Let me save this. Forget semicolon. Okay, fine. So very simple program I have written there. One variable of type PID underscore T, because if you open it here, you can check it. Fork returns PID underscore T. There is no parameter required, and fork is the system call. And this PID underscore, so this is the type. Okay. Now, this is the call in the operating system which will be invoked only once and it returns twice. Right? Interesting, no? I'm calling the function only once, but it will return twice if it is successful. Why? Reason is very simple. Fork creates a child process, so it returns PID. So for a parent, it returns PID of child process, and for child it returns 0. And if it is not successful, it returns negative value, so less than 0. In case of error, it returns value less than 0. So that is a negative value. Now let us save this, and I'll try to execute this code. I save this as a fork.c. Let me see where I am cd hello up, cd src, then hello up, and fork.c is there. Fine. So let me compile this using go with GCC or CLang, doesn't matter. So GCC fork.c, yes, compiled successfully, and now execute it. Interesting. It showing hello only once, that is by the parent process, but next printf, that is by, will be displayed by both now, by the parent process, by the child process. Now again you may wonder here, because if fork creates duplicate copy of its parent, why hello is not printed, right? Reason behind that is very simple. The reason is, at the time of executing fork, which is on line number 10, the program counter has the value of 10, for example. Right? So even though hello is also instruction available in child process, the value of program counter was 10. So when child is scheduled, it will start executing from line number 11. So it don't display that hello part. Okay. Anyways, we'll see in depth this part. Right now, let me stop sharing. Okay. Any doubt there? Any doubt there? Because it is now just 1 minute remaining. So if you have any doubt on process creation, fine, still we need to see how to give separate task for parent, separate task for child, Okay, fine. So we'll stop here.